All right, so we are now going to discuss the fundamental theorem of algebra. And morally, what the fundamental theorem of algebra says is that C has all zeros of all polynomials, of all non-constant polynomials. Of course, if your polynomial is constant, the only way for it to have a zero is if it's the zero polynomial. So you have to have like degree at least 1 in order to have a zero. But C has all zeros of all non-constant polynomials. In algebra, we say C is algebraically closed. You can't possibly add in any more zeros. You already have them all. Right? That's what we say in algebra. Um, all right. So, finding solutions of polynomial equations, done, because C has all of them. No, that's not true. We don't have formulas for them. We know that they exist in C, but what are they? Where are they? How do we find them? Okay, and can we even find zeros in general with formulas? So not quite done, but the fundamental theorem of algebra is important. I have a complex analysis class on YouTube that you can look at for the proof of the fundamental theorem of algebra, or you can look at the proof in your book, or you can look at the notes on Canvas, or the previous time I taught this on Canvas. I think I proved it in that class. I'm not going to prove it. I am just going to give you the idea behind the proof. So the idea is simple. Is suppose that P of t rather, well, this is stated with z. P of z is a polynomial function, non-constant, of course. Such that P of z is not 0 for any z in C. So you can never, ever, ever, ever get 0. Then what? Well, then the modulus of P of z squared we can view as a function from C to R. And since it's never 0, we can actually deduce that it has a non-zero lower bound, and in particular a positive lower bound. In particular, we can do some stuff and deduce that this has a global minimum. Okay? So there is a minimum value that this achieves, an absolute smallest value. So if we were to draw C, okay, again, I'm brushing things under the rug. Okay, I guess the domain doesn't necessarily have to be there, but if you were to draw C on a big enough, let's say the minimum's at some point W, on a big enough ball centered at 0, W is, you'll be able to find W there somewhere. Okay, so you draw a big enough ball. And if we were to zoom in on W, so we're going to stick another ball inside of W, and we're going to zoom in on that one. Okay. All right, then what we do is we probe sort of radially and we sweep out. So we probe radially, this is our theta parameter, and we sweep out an angle. Okay? And what you can do is you can probe with theta and r, and you can deduce, you can find some W naught such that the value of the polynomial, the modulus squared of the polynomial at W naught is strictly less than P of W. And that's the contradiction. Okay, so we've contradicted we have a global minimum. And the exact details of that are going to be left to you to read. And then of course I do have the if you go to my channel you can find the complex analysis course. But that's the idea. And again, this is not a course of complex analysis. We're not going to prove that. But the idea is simple. Deduce it has a global minimum. This function has a global minimum, and then contradict that by sweeping out with an appropriate theta and r, and then some analytical computations.